Hello everyone, welcome back to my another video. Today in this video I will be teaching about the chapter circle. Uh, this video will be specifically dedicated to class 10 graders or any secondary level students. Now let us talk something about relationship between inscribed angle and its corresponding. Here by inscribed angle I'm suggesting in this circle ACB, the inscribed angle will be suggested by the angle AOB, which would be this angle, and another inscribed angle in this circle as shown in the figure would be angle ACB, which would be represented by this angle. We are going to derive the relationship between these two angles, which would be angle AOB and angle ACB. Here at the in the another slide I will be going to discuss about the relationship between these two inscribed angle, which would be as a angle AOB is equals to 2 multiplied by angle ACB. I will be deriving this relation in the another video, in the another slide. And now moving on to the derivation of the relationship between the two inscribed angle, which is suggested by the angle AOB and angle ACB in this circle. Now let us move on to the isosceles triangle OAC. In the as we all know that the sum of the angle in any triangle is equals to 180 degree, which is suggested by this strap, which is angle OAC plus angle OCA plus angle AOC is equals to 180 degree. An isosceles triangle is a triangle having two angles same. Here in this triangle OAC, and the angle OAC and angle which would be this angle and this angle is same, so we can write angle OAC is equal to angle OCA as suggested by this equation. Now replacing the value of OAC with angle OCA, we get 2 angle OCA is equals to 180 minus angle OAC, which would be our first equation. Similarly, we calculate with the similar process and taking on the similar steps, we will get the equation 2 as well. Now adding the equation 1 and equation 2, we are left with this step. We are left with this equation. Here angle OCA plus angle OCB would be angle OCA, which would be this angle, and angle OCB which would be this angle, which is certainly angle ACB. Here we get it. So we replace angle OCA plus angle OCB by angle ACB, and similarly the angle angle AOC. Angle AOC would be this angle, and angle BOC would be this angle, which would be summing these two angles would be combinedly referred as angle AOB, which is suggested by this step. So we can replace angle AOC plus angle BOC by angle AOB. Now this whole angle would be 360 degree, and 360 minus angle AOB, which would this angle AOB would be this one, and subtracting 360 degree from this angle, subtracting AOB from 360 degree, we are remain with this angle, which would be also indicated by angle AOB. Here we have derived the relationship between the two inscribed angles as suggested by this step. Let us go through the theorem 1, which would be the central angle is double of the inscribed angle based on the same arc. We have already described and derived this relationship between the central angle and the inscribed angle on our previous slide. You can go over through that slide if you have missed it. If you want me to make you understand this slide once more, let me know in the comment section down below. Now moving on to the next theorem, which is suggesting us to show that the angle in the circumference of the semicircle is a right angle. By that it means in this circle ACB, it's suggesting that angle is suggesting that the ACB is a semicircle, and the angle the angle suggested by the angle ACB is a right angle or 90 degree. We have to prove that. Now we have been given that O is the center of the circle, and AOB is the diameter of the circle, and we have been given ACB as a semicircle with angle ACB as a circumferential angle, which we need to prove that it is a right angle or 90 degree. As we have proved that, we have already derived that the inscribed angle is half of the central angle. Here in this case, the central angle would be angle AOB and the inscribed angle would be angle ACB. They have these two angles, central angle and inscribed angle, have the same base, which would be AB. So we can write as a statement 1, angle ACB is equals to angle 1 by 2 of angle AOB, which is the mathematical indication of the reason that is inscribed angle is half of the central angle. We have derived this equation in our previous slides as well as the theorem 1. Now we can write angle AOB is equals to 180 degree in our statement 2. Since AOB is the diameter of the circle, the angle occupied by it would be angle 180 degree. Now solving the statement 1 and statement 2, we have putting the value of angle AOB in the statement 1, which would be a 180 degree. Half of 180 degree is equals to 190 degree, and here we have it, angle ACB is equals to 90 degree, which is a right angle. Here we have proved that the angle of the circumference in a semicircle is always a right angle. Now moving on to the theorem 2. This theorem says that the angle says us to prove that the angles on the circumference of a circle based on the same arc are equal. Here in this circle ACDBP, AB is a arc, is the similar arc for angle ACB and ADB. Here the angle ACB and ADB are the circumferential angles which touches the circumference of the circle at the point C and D respectively. Here we have given O is the center of the circle and AB is the similar arc. As I have said that AB is similar arc for the angles ACB and angle ADB. Here we have to prove angle ACB and angle ADB are equal, which are the circumferential angles. To prove that, first we have to join A with O and O with B. So we have got our central angle. Now remembering from our previous theorem that the central angle is twice the inscribed angle. Here angle AOB is the central angle, and the two inscribed angle we have angle ACB and angle ADB. So similarly we can write angle AOB is twice of ACB, which is suggested by the theorem 1 and this equation statement 1. And similarly we can write statement 2 as angle AOB is equal to twice of angle ADB, which is also based on the theorem 1 that the circumferential angle or the inscribed angle is half of the central angle. Here equating the statement 1 and statement 2, we get angle 2CB. Angle 2CB is equals to angle 2ADB. Now cancelling 2 on both sides, we get angle ACB is equals to angle ADB. Finally we have proved that angle ACB and angle ADB, which are the circumferential angles on the similar arc AB, AB are similar in value, angular value. Now moving on to the theorem 3, it suggests that the opposite angles of a cyclic quadrilateral are supplementary. By saying supplementary, it means that we have to prove that the opposite angles of a cyclic quadrilateral is 180 degree. Here a quadrilateral is a shape having 4 sides. A cyclic quadrilateral in particular means that all the 4 sides of the quadrilateral touching the circumference of the circle as suggested by this quadrilateral in this circle ABCD. Here ABCD is a cyclic quadrilateral, and we have to prove that the angle ABC, which is suggested by this angle, and angle ADC, summing up these two angles, we should get a supplementary angle or 180 degree angle, and adding DAB and angle DCB, we should get summing up these two angles, we should get a sum of 180 degree. We have to prove this. Now moving on to the proof that the opposite angles of cyclic quadrilaterals sums to 180 degree. Here we need to understand firstly that the angle AOC has two angles. Angle AOC, this angle would be called as obtuse angle AOC, and this angle suggested by two lines would be called reflex angle AOC. Now using theorem first, which says that the central angle is double of the circumferential angle or the inscribed angle. Here we have arc AC. On the arc AC, here we have on the arc AC, we have the central angle as angle AOC and the circumferential angle as angle ADC. Now we have to look on the obtuse side of angle AOC first, which is suggested by the statement 1, and moving on to the next statement. Now we have to look for the reflex angle of AOC, which is represented by this part. The reflex angle of AOC is twice of the angle ABC, which is suggested by the statement 2. Now on the third statement, it's a simple arithmetic addition. Now we add the statement 1 and statement 2 on the third step. Now we get angle 2ADC plus angle 2ABC is equals to obtuse of AOC and reflex of AOC. Okay, taking two common on the here the addition of the obtuse side of the angle AOC and reflex side of angle AOC. Here we can see that it forms a complete circle, so it equals to 360 degree, which is suggested by this step. Now after solving this equation, we get angle ADC plus angle ABC is equals to 180 degree, which was our statement and which we have proved it. Now similarly we carry out this similar proof methods to prove that angle DAB plus angle DCB is equals to 180 degree. For that case, we have to draw a line. For proving that angle DAB is equal plus angle DCB is equals to 180 degree, we have to draw a line connecting angle DO and angle OB, so that it would be easier for us to prove this statement 4. Now we carry out the similar step to prove the statement 4. Now moving on to the Q&A. Here we have our first example or first question. Let us go through it. In the given figure, angle PQR means this is given as 100 degree, and points P, Q and R are our circumferential points of the circle with the center O. What is the value of OPR? Find. We have to calculate this value, angle OPR. Now we have to remember our theorem first, which suggested that the central angle is twice of the inscribed angle. Here our central angle would be this angle, which would be reflex of POR, and our inscribed angle would be angle PQR, which we have been given as 100 degree. Now moving on to this statement, moving on to the calculation, reflex angle of POR is equal to twice of PQR, suggested by our theorem 1. Now we have been given the value of PQR as 100 degree. Putting the value of PQR, and now we have got that PQR is equals to 200 degree. Now as we know that the reflex of POR and a reflex angle and the obtuse angle of POR is equals to 360 degree, which forms a complete circle, which is suggested by this step 2 here. Now we have got reflex angle of POR as 200 degree. Putting the value of reflex angle POR as 200 degree, we obtain the obtuse angle POR as 160 degree. Now moving on to our third step, it's the last step. Then after we can get the value of our OPR. As we all know that the sum of all three angle of triangle is equals to 180 degree. Angle in here OPR triangle is isosceles triangle, since it has two sides equal, being the radius of the circle OP and OR. In the isosceles triangle, angle ROP and angle OPR plus angle PRO is equals to 180 degree, which is suggested by this equation. We have calculated the value for POR as 160 degree, putting the value of this in the next step. And since triangle POR is an isosceles triangle, the angle OPR and angle OPR and angle ORB would be the same. Replacing the value in the next step, similarly we get the step as 2 angle OPR is equals to 180 degree minus 160 degree. Similarly on further arithmetic calculation, we have obtained the value for OPR as 10 degree, which is our solution, and we finally have found the value for angle OPR. Now moving on to the next question. Here we have given a circle. ABCD. Let us read the question first. In the adjoining figure, angle ABC is 74 degree, angle ACB is 30 degree. Then find the value of BDC. We have to find the value for ADC. First we have to find the value of angle BAC, and then remembering the theorem 2, that the circumferential angles are same if they are on the same arc BC. Here we have the same arc BC. For the two circumferential angle BAC and angle BDC, we can apply theorem 2 for solving the value of angle BDC here. For that, we have first determine the value of angle BAC as suggested by the step 1. As we all know that the sum of angle of any triangle is equals to 180 degree. Here angle ABC plus angle BCA plus angle BAC is equals to 180 degree. Or we have got the value for angle ABC is which is 74 degree, and angle ACB is 30 degree, as we can see on our next step. And we have to determine the angle BAC is equals to 180 degree. On the simple calculation and arithmetic operations, we find out the value of for ADC is equals to 76 degree. Since from our theorem 2 we can say that the angle BAC is equals to angle BDC, which would be 76 degree. Here we have found out the value for angle BDC, and we have solved this question as well. Let us move on to the example 3. Let's just read the question first. In the adjoining figure A, B, C, and D, there are A, B, C, and D are 4 points on the circumference of the circle. The chords AC and BD are intersecting at point E. Point E, if angle BEC is equals to 30 degree and angle ECD is equals to 20 degree, find the value of BAC. Here we have to find the value of angle BAC. For that, we have to first find out the value of angle DEC, which is represented by this angle. For that, as we all know that the sum of angle in a straight line is always 180 degree. So angle BEC plus angle DEC is equals to 180 degree, which is suggested by this step. We have given angle BEC is equals to 130 degree, and applying the arithmetic operations, we get the value for CED as 50 degree. As we all know, the sum of the angles of a triangle is 180 degree. We apply this theorem on the triangle EDC. Here angle DEC plus angle ECD plus angle CDE is equals to 180 degree. As we already have the value for the two angles of the three angle of the triangle, we can obviously calculate the remaining angle, which is EDC. Now we have got the value for EDC as 110 degree. Since angle BDC and angle BAC are on the similar arc BC, and as suggested by our theorem 2, the angle BAC and angle BDC, which are on the similar arc BC, should be equals. So finally we have got the value of BAC as 110 degree, which is equals to angle EDC. Now let us move on to the example 4. In cyclic quadrilateral ABCD, the diagonals AC and BD are intersecting at a point A. If angle DBC is equal to 70 degree and angle BAC is equal to 30 degree, then find the value of BCD, and also if sides AB is equals to BC, what is the value for angle ECD? Here we have been given a circle ABCD and a cyclic quadrilateral ABC, and we have given these two angles, and we have to find the value for angle BCD and finally we have been given AB is equals to BC, and we have to find the value for angle ECD, this one. For solving this question, we have to remember our theorem 3, which suggests that the sum of the angle for sum of the opposite angle for the cyclic quadrilateral is equal to supplementary or 180 degree. Now let us first go on our first step. On the arc CD, there are two inscribed angles, which is angle DBC, which is angle DBC, this represented by 70 degree, and angle DAC. These two angles are similar. So angle, we have got angle DAC is equals to 70 degree as well. Now moving on to our second step, we calculate the angle DAB, which is the sum of the angle BAC and angle CAD, which is represented by this section of this cyclic quadrilateral, which will be 30 plus 70 degree, and we have got the final value for angle DAB is equals to 100. Now we have to apply the theorem 3 for the angle BCD and angle DAB, this one and this one. The sum of these two angles is equals to 180 degree. We have the value for BAD as 100 degree, and the value for BCD has to be determined. Putting on the value on this equation, we get the value of BCD as 180 degree minus 100 is equals to 80 degree, which is the solution of our first part of this question. Now moving on to solving the second part of the question, we have to find the value for ECD as represented by this section. Here we have been given by the question that angle AB and sides AB and BC are equal. Since the side AB and BC are equal, the angle BAC, which is 30 degree, and angle BCA, which will also be 30 degree. Now we have got the value for angle BCD, which is represented by this section. Now, having known the value of angle BCD, angle ECB, which is 30 degree, we can calculate the value for angle ECD respectively, which would be 50 degree after operating the arithmetic operations as shown in these steps. Now moving on to the example 5. In the given figure, alongside ABCD is a cyclic quadrilateral. If the side AB is produced to the point E, then prove angle ADC is equals to angle CBE. Here we have been given that ABCD is a cyclic quadrilateral, and the side AB is produced to E. For solving this question, we have to remember the theorem for cyclic quadrilateral, that the sum of the opposite angle of cyclic quadrilateral is equals to 180 degree, and we have to remember the simple formula for a straight line. Moving on to statement first, which would be based on the theorem third of this theorem third, which I had discussed in my previous slides. Angle ADC plus angle ABC is equals to 180 degree, and remembering the formula for a straight line, the sum of the angle is 180 degree. Angle ABC plus angle CBE is equals to 180 degree, which is suggested by the statement 2. Now we get equating statement 1 and statement 2, we can get the statement 3. Now cancelling the similar term on the equation, which is angle ABC. Now we have finally got our answer, which would be angle ADC is equals to angle CBE. So solving this question will require the combined knowledge of the theorem third for cyclic quadrilateral and the knowledge of the straight line. And this is the end of the video. Thank you so much for watching my video till now. If you have any queries regarding this video or the previous video, please let me know in the comment section down below, and I will be coming up with the related mathematical contents for secondary level as well as higher secondary level or bachelor level in the upcoming videos. So